Well, howdy! So today I'd like to talk about angular collisions. What are angular collisions? Well, an angular collision is something like this sort of illustration up in the upper left-hand corner, where when one thing hits another thing, in this case a ball hits a stick, one or the other one of them starts to rotate. So you'll notice that in this particular case, the stick starts to rotate after it's been hit on the end by this ball. That's what makes it an angular collision, is one of these things is rotating in at least one of the situations, before or after. Possibly the rotation changes its character. Possibly you have two spinning balls that hit each other, and when they come out, they have a different angular speed when they come out, something like that. So whenever there's a change in the angular character, the spin of an object, that's what we really care about in this angular collision. So how is that going to work? Well, that's going to work because angular momentum is going to be conserved for these. That means the orientation of the objects is not fixed, right? If there's an external torque that keeps everything in the same orientation for whatever reason, then you're not going to have conservation of angular momentum. If you're dealing with point particles, like basically we were in Unit 3 when we were talking about conservation laws all by themselves, or conservation laws for point particles, in that case, then we don't have to worry about conservation of angular momentum. It's still viable, right? There is a translational angular momentum, right? But in the case of the point particle, we really only have to worry about conservation of momentum. Now, with angular collisions, you can violate conservation of momentum as long as angular momentum is conserved. So how would this work? This would work if you have a door, for example. If you hit the door with a broom and the door opens, that could be a angular collision. Maybe not with a broom, maybe with a ball, like a basketball or something, and you open the door with the basketball by throwing the basketball at the door, then you have an angular collision. One of the sides of that door is attached to the wall. It's got hinges on it, right? And those hinges fix the axis of rotation. And because that axis of rotation is fixed, there's an external force on that object, and therefore the momentum is not conserved. Okay, so that's one thing that we'll see in the homework. In the homework, you'll really only have to worry about the conservation of angular momentum, and you won't have to worry about the conservation of momentum. So what I'd like to do is I'd like to go through an example, and hopefully by going through this example, we're going to get an idea about how this works. And this is the example. The example are these dumbbells. So we've got a couple of dumbbells here that are coming after each other, and the weights are going to hit each other. This bottom weight of the left hand dumbbell and the top weight of the right hand dumbbell are going to hit each other dead on in the center of those weights. And then after they come apart, down here, they're going to leave with the same speeds. So the dumbbells are identical. They're both 10 pounds, 20 pounds, whatever. And when they hit each other, they just go off in the other direction. Now this is exactly what we saw with a point particle when we had two identical point particles hit each other with the same velocity. They went out away from each other with the same speed in the opposite direction, with opposite velocities as they came in with. So this is something we've seen in our point particle collisions. So we'd just like to illustrate this a little bit as we go along. So let's illustrate this. Just look at what happens here. And that looks pretty wonky, right? That doesn't really look correct. And why doesn't it look correct? Well, because we do know that these things are supposed to spin. We've seen things like this happen previously. We may not have seen it in this particular format, in this particular example, right? We maybe don't have little spherical weights on dumbbells that we bash into each other just for fun. And I've tried this with some weights, and it's a bit of an issue. There's some problems with it, but it's a hard experiment to set up, so I don't have any video. However, this is a good way to look at this thing. So we look at this, it looks funny. So that is not what we want to have happen. Let's see if we can set this up and figure out why it didn't work. So let's start here just by calculating several things. Kinetic energy before and after the collision, momentum before and after the collision, angular momentum before and after the collision. And see, are these quantities conserved? Kinetic energy, well, basically yes, right? We have for each one of these two masses, m, if this is a 10-pound weight, this is 5 pounds here, 5 pounds there, 10 pounds, 2m, right? And it's got that velocity v, so that is 1/2 2m v squared as the kinetic energy for one of these dumbbells. Then we have to add in the other dumbbell, right? 1/2 2m v squared. If we look after, again we have 2m's going at the speed v, so we have 1/2 2m v squared as the kinetic energy for the final situation. That's 2mv for each case. Very nice. We can do that. That's easy to do. All right. The momentum. The momentum is conserved as well. So we're looking at that momentum. And what do we see? Well, we see that the momentum in the x direction is for the left-hand dumbbell 2mvi in the initial state. For the right-hand dumbbell, it's 2mv minus I. It's going in the opposite direction, minus I. Add them together, the momentum is 0. Total momentum for the system is 0 before the collision. After the collision, we have 2mv in the negative x direction now, so that's 2m times negative I. Very good. Over here we have 2m times positive I, right? The velocity is going in that other direction, 2mv times the positive I. Add them together, you get 0, everything's good. Again, at this point, we've done everything the same as we would have done when we analyzed the point-particle collision. Now we want to go into conservation of angular momentum. And that does not seem to have been conserved. So what's going to happen here? Well, we can analyze this with L equals R cross P. That's probably the easiest way to do this because nothing's really spinning, right? So that's pretty easy. And we're going to use as our analysis point this spot right here, the spot where the two weights come into contact, where the collision actually occurs, where the contact occurs. So when we look at that, what do we see? Well, we see that this distance here, the length of the dumbbell, times mv is the angular momentum for this particular bit here. And then this lower weight on the left-hand dumbbell has no angular momentum. And why doesn't it have any angular momentum? It doesn't have any angular momentum because it's traveling on this line here for where these two things meet, for where the two dumbbells collide. So if it's traveling on that line, directly on that line is our 0, right? So we have, instead of MVD, we have MV0. So for this entire dumbbell, the entire angular momentum comes from this upper dumbbell because we're going to analyze it at the most convenient spot, which is the place where the two dumbbells meet. So that's MVD minus K. All right, and the minus K is going to come from the cross product. How about the other direction? Well, this also has the same character. It's going to be minus K, and for all the same reasons, it has 2mvd as its angular momentum. So we have minus 2mvd in the k hat direction as the angular momentum. K hat coming out at us. It's not going up the screen. It's coming up. It's coming towards you because this is the x direction. That makes this the y direction. Third direction is k out at you. This is the axis that's going, from your eye. The axis is going through your eye to this point on the screen where the two dumbbells meet. That's the k-axis. That's the z-axis. Okay, so what happens afterwards? Well, what happens afterwards is you can see that the dumbbells have the opposite character. Rather than going clockwise as they originally were, they're going counterclockwise. But otherwise, everything else is the same. So because they've switched that direction, because they're now going counterclockwise in character, you have 2mvd. So we get a change in the angular momentum in this initial situation. So that's something we don't really want. There's no way to change the angular momentum. There's no torques in this situation, no external torques in this situation. There's nothing that's doing anything to these dumbbells that make this angular momentum change. That is, by the way, the reason why the experiments where I take my weights in the garage and I try to banging them at each other, where that doesn't work very well, because rather than being these nice spheres that roll nicely and do everything I want them to do the right way I want them to do it, what happens instead is, they're cylinders, and they're not even just cylinders. They're, stacked up 3 at a time. It's hard to get them to hit it exactly right, and then when they do hit, they're not really that tight, and there's some ringing, and there are all sorts of little problems. So there are external torques in that one, some sort of frictional forces that make things not work quite the way I want them to. And of course, again, they make loud noises, and that bothers my wife. So that's the situation we don't like, right? Now, we have analyzed it. We've seen that energy is conserved. We've seen that momentum is conserved. We need to see how we can conserve angular momentum. And of course, the way we do that is more or less to assume it's conserved and see what happens, right? So our requirements for this are going to be that the momentum is conserved, and that's because there's no external force on the system. We're going to require the angular momentum to be conserved because there's no external torque, and we're going to take an elastic collision, right? There's going to be no loss of energy in this situation. Could also have a totally inelastic collision if we wanted to. That would be kind of difficult in this case. But we're going to look at the elastic collision. You're going to look at inelastic collisions in the homework, and I think they're probably totally inelastic. And what's going to change in the homework is, because you're just going to be dealing with rotating things, rather than matching the velocities, you might be matching angular speeds. And in one case, you'll make a match between an angular speed and the speed of an object, because you'll have a bullet hitting a board or something like that. So you'll have to do something like that, but that'll still be a totally inelastic collision because they'll both be moving with the same velocity afterwards, because something's going to embed itself into something else. So you'll have to deal with some of these totally inelastic collisions in the homework, But what we're going to do is focus on the elastic collision. All right. Okay, so how we're going to fix this previous example? Well, what we're going to have to do is we're going to have to modify this after picture. So how we're going to modify that after picture? We're going to start having things rotate. And we've got our three separate conditions here. Momentum is conserved, kinetic energy is conserved, angular momentum is conserved. The momentum is the first one that we're going to want to look at, and that does a little bit of work for us. Basically, all that really does for us is, because the initial and final momenta are the same, we're going to find that v1 and v2 are the same. They're just whatever it is, the final velocity, right? So we have an initial velocity v, we have some final velocity coming out vf. Now, we'll find out what that velocity is later. We're going to have to use conservation of kinetic energy and conservation of angular momentum for that. Conservation of kinetic energy. Well, we've got two parts in the final state. So in the initial state, we have basically the same deal with the kinetic energy that we had initially. In the final state, what we're going to have is the translational kinetic energy as well as a rotational kinetic energy, which has an I in it, and we'll assume an I at the very end. But for this part, we're just going to say I is I, rather than take a particular form of it. We'll take a simple one at the end to give us some numbers, because everybody loves numbers. And that's going to have something to do with the angular speed. So that's going to give us that. Then we will have our angular momentum. Now we have, for the angular momentum, the minus 2 mvd that we had previously. Then when it comes back, we have the mvd that we had previously, as well as an I omega. And I'm going to subtract the omega right away just for fun. So I don't have to remember something about it later. Anyways, this is going to be negative because the omega is basically pushing this guy in the opposite direction. This guy is going in the counterclockwise direction here, so it's negative just like the initial angular momentum. It's in the clockwise direction, not counterclockwise, excuse me. So, to figure out what Vf and omega are, we're going to use the kinetic energy and the angular momentum. We've actually already used the momentum because that gave us something nice and easy, this Vf being the same for both of them. And when we combine these things, I don't want to do the math, but I'd like you to see what happens, is we get from 3 alone, Vf is I over md omega minus V. And for omega, what we have to do is we have to play with equations 2 and 3 together. That gives us 2 over this awful quantity, 1 plus I over 2md squared times V over d. That is our omega. So these things together are what give us Vf and omega. We have to calculate omega to get Vf. And actually, we could just plug this in over here and we'd have a nice complicated equation and everybody be really happy, right? Because that's what we love. But really, we need to wait just a little bit in order to do that. It's a little bit nicer, let's say, if what I do is I include a smaller thing. So what I'll do is I'll use very small weights on these dumbbells. So I'm going to assume these are point particles at the edge of this rod, of the handle. And so I don't have a very complicated I. I've just got m times d squared, the square of d over 2, 1/4 md squared. So when I take that, I get much simpler expressions. Not super simple, but much simpler expressions. That give me 8/5 v over d as omega and minus 3/5 v as the final velocity. So I've got these two situations here. Very simple, very nice. And that basically gives me what we have here. That gives me a situation where, and you can check this out if you'd like, the kinetic energy and the angular momentum are conserved, as well as, of course, the momentum. This is not so hard to do, not so hard to believe, because I constructed these to be that way, right? So all I had to do was get the algebra right and everything was fine. And I've plotted this because this is physics and we like plots. And we can see that if I, possibly this should have been a D, if I plot I over md squared and I plot the solution that I got for the omega there, we can see omega is coming out like this. You have VF coming up like that. And these are all relative to V or V over D. So that gives us our a plot that shows that as we get something with a larger and larger moment of inertia, omega reduces and so does VF. And so let's take a peek at what this looks like if I plug those numbers in. That is one amazing dance, right? That is exactly what we were expecting. So that is what conserving momentum, kinetic energy, and angular momentum actually give you. So we put all of those things in, and we can actually construct a situation that looks fairly close to the real thing in our angular collision. Okay, so we just have to remember that angular momentum is conserved as well as momentum. Sometimes they're not conserved, and that's when either there are external torques, which invalidates the conservation of angular momentum, or there are external forces, which invalidates the momentum. In the homework this time, this one's going to be invalidated, right? We're going to have some fixed axis of rotation, like an axle or some hinges or a pivot or something like that. And that will cause momentum conservation to be violated. So hopefully that's sufficient for you for looking at this particular situation, the angular collisions. I think it's fairly important, and I think it's very interesting. So I hope you found this useful. I'll talk to you again next time. Bye now.